For this next section, we have 4 questions. There's also a question 26, but I'm saving that for the graphing part of the videos. For number 22, if a quadratic function has 2 x-intercepts, that means that it has 2 real solutions. Once again, the board is acting up. 2 real solutions. So that means that there are no pure complex solutions. Because complex numbers, once again, that's in the form of a plus bi, where it has a real term and an imaginary term. But if you have 2 x-intercepts, that means that if you set the equation equal to 0, you will find 2 real solutions. And since they don't have an imaginary part, quadratic functions with 2 x-intercepts have no purely complex roots. Their solutions are complex, but they're not purely complex because they do not involve a real and an imaginary part. For number 23, if a quadratic function has no x-intercepts, how many purely complex roots does it have? Well, it could have 2 or it could have none. But for this instance, more likely than not, it will have 2 pure complex roots. Pure complex roots. Because you have no x-intercepts, you're going to end up with a solution that includes I. So your solution includes I. If your graph has a vertex at the y-axis, at the y-axis, it'll have 2 pure imaginary roots. So that's at the y-axis and no x-intercepts. If your graph is located anywhere else with no x-intercepts, then you will have 2 purely complex roots, because the solutions include I. Quadratic cannot have one purely complex root. Complex roots always come in pairs. Always come in pairs. More specifically, these pairs are called complex conjugates. Where if one solution is a plus bi, the other solution is a minus bi. So for number 25, if one of the solutions is 3 plus 1, that means the other solution, 3 plus I, the other solution is 3 minus I. So to write the quadratic in factored form, that's a x minus solution number 1 times x minus solution number 2. We're given the a value is 1, set the equation equal to y. That is really not liking me for this video. Set the equation equals to y, so we have 1 times x minus the first solution that was given to us, 3 plus I, times the second solution given to us, 3 minus I. And that is equal to y. This is the quadratic in factored form. this would be the final solution. But also I want the quadratic in standard form, so we need to expand this out. To expand out, let me fit this to, fine. To expand out quadratics that have complex roots, we want to triple distribute, or triple FOIL if you choose to call it FOILing over distribution. So that would be x minus 3 minus I times x minus 3 plus I. So to multiply this all out, you would do x times x times negative 3, x times I. So x squared minus 3x plus ix. Then you would do negative 3 times x, negative 3 times negative 3, negative 3 times I. So negative 3x plus 9 minus 3I. And last but not least, negative I times x, negative I times negative 3, and negative I times I. That would be negative ix plus 3I minus I squared. And I squared, as we stated in previous videos, is negative 1. So I can change negative I squared to become plus 1. And that's this last term here. So now we combine all the like terms together. X squared is the only x squared term. Negative 3x and negative 3x combine together to become negative 6x. Ix and negative ix cancel each other out. Plus 9 and plus 1 combine together to become plus 10. And then the negative 3i and positive 3i cancel each other out. So here's the final equation in standard